About 5 years ago, we were challenged by Neil Blue, who's the CEO and chairman, to look at a reactor that could produce electricity at a competitive price within the energy mix in the United States. He also wanted a reactor that would be compact enough that it could be shipped on a truck on the U.S. highway system. He also asked whether we could design a reactor that could burn for decades without refueling. This gave rise to a new reactor design called Energy Multiplier Module, EM2. From GA's point of view, there are two major challenges facing nuclear. One is we've increased the scale of nuclear reactors, the size, in order to be able to drive the price of electricity down. But in doing so, the capital cost is dramatically increased, largely because of the material and complexity of these reactors. This has led to reactors that cost on the order of $10 billion each. There are very few utilities in the United States that can afford them. The efficiency of nuclear power plants has remained relatively constant over a considerable period of time. They've topped out at about 34%. Other forms of energy generation like coal and natural gas, much higher. Coal is at 45, natural gas is at about 63%. So they're capturing more of the heat and turning it into electricity, which improves the price point of electricity. So we were driven to thinking about how we can create a compact reactor that could produce enough thermal energy that could be efficiently converted into electricity. And the problem you have is that when you reduce the size of a reactor, you reduce the volume. And if you reduce the volume, the thermal power goes down. And so the question was, how do we maintain high thermal power? I can't tell you the nature of the design. It took us a long time to figure this out. It's an unconventional core design that enables a uniform burning of the core. And we don't have to reshuffle fuel. Once you put it in there, it'll burn. And it'll burn uniformly. That's a major advantage. We don't touch the core. We can seal the core. That actually has a proliferation advantage in that if you open the core, you're going to have a good reason to open it. So if you have a fuel that's in a reactor for decades, one core that's burning for, let's say, 30 years, in that same amount of time, a light water reactor will have changed its core 7 times. This automatically tells you that the amount of waste that this reactor produces is far less than that of a light water reactor. It's 80% less than a light water reactor. The premier laboratory in the United States for silicon carbide is Oak Ridge National Laboratory. And so we are currently testing silicon carbide in our fuel at Oak Ridge. We understand the properties of the material. We understand the properties of the uranium carbide fuel. We have predictions about the behavior of both the fuel and the cladding. We have done the simulations of the core, and Argonne National Laboratory independently did simulations of our core. And the laws of physics tell you what to do. And relying on the laws of physics is a pretty good bet. The thing about gas reactors is they have a long history, and as far as non-light water reactors are concerned, they've probably made the most progress in terms of licensing. And so a lot of the licensing issues associated with EM2 will, at least in part, have already been dealt with through the licensing of gas reactors. And I'll remind you that GA has built 2 gas reactors. One is Peach Bottom, and the other was Fort St. Vrain. There are a number of key innovations here that I think will change the game in nuclear energy. One is the fuel, and along with that, the core design. The other is the power conversion unit that goes along with this, because that's where you make your money. The next most important, in terms of a sensitivity analysis, is efficiency. That's where you capture your dollars, because you're paying a lot of money to generate the heat. If you don't convert the heat into electricity, you're missing the point. We've gone through a very detailed financial analysis of EM2. We followed the updated MIT methodology for costing out the reactor. We went out and we did bids on all the components in it, major components. We made standard assumptions about debt rate, depreciation, all those things. So an advanced light water reactor is about 11 cents per kilowatt hour. We can get down to 6.5 cents per kilowatt hour. I would hope that the United States, who invented nuclear reactors and has also led the world in major advances in technology, would also look at the need for a paradigm shift in the way we approach nuclear. I think it's within the American spirit, to do that, and GA is an example of that. We wouldn't have embarked on this if we didn't believe that there was an opportunity to make a major advancement. We're a private company. Money is very precious for us, and we're only going to devote it to things that look sound from the point of view of the fundamentals that drive the innovation. Otherwise, it's pointless. This is a classic case of something that the government should do, because the high risk associated with doing it and the time scales for recovery of capital are such that it makes it very difficult, given all the constraints that are imposed on nuclear, to do this on its own. So that in 12 years, we will have a commercial prototype producing electricity, and we will have a factory that will produce the cladding. We will have a factory that will produce the fuel for the first core of the first reactor. But in order to be able to do that, we have to be able to reduce enough of the risk in it to be certain that moving forward with the large investment, which is to build a prototype, is financially sound.